fractals are the idea of very chaotic behaving shapes. Okay, a lot of times, like when you look at the branches of a tree, you look at the the leaves of a tree, you look at the veins in somebody's hands, you look at the tracheal tubes in somebody's lungs, lightning across the sky, clouds, even like tracking the stock market. All those things kind of have a fractal component to them. Okay, kind of just do a quick Google search of a fractal here. Let's see some images. These types of things. You ever seen these? Okay. These are fractals. Okay. And the idea, I don't know if I had a program that showed these, and it really showed the idea behind them. But basically, the idea is if I've got a fractal here, I should be able to kind of zoom in on like these branches here and continue to zoom in infinitely many times and still kind of get the same image to show up. Does that make sense? If you start looking at like a snowflake, that's you said that's in that movie. A snowflake. Okay, is kind of that fractal idea. Okay, you kind of see that happening here with these pictures, right? Okay, if you were to take take a snowflake on your hand and look at it, that's what's going on. Here's some real ones here. But fractals are very useful. Let's see if we can get. Let's see if I can get a real life use of fractals. See if we get some images here. Not fractals. That says fractals. Last class I had some pictures here. All right, so you can see, the ups and downs, the rise and falls of the stock market are kind of jagged, uniform kind of relationships. Okay, they talk about if you're doing any reading of fractals, a lot of times the comparison is like the mapping of a coastline. Is jagged but can be comparable to some type of fractal. If we look at spell lightning, right? Still knows what I want. But the idea of lightning across the sky, they're a fractal. And now that kind of looks like branches of a tree, right? We do branches of trees. The idea is that these are showing fractal relationships. Okay, and then so anything that kind of does that. So like the branches of a tree. If you ever seen pictures of lungs, okay, the tracheal tubes in your lungs. If you've seen like veins in a hand or something like that, those types of things kind of have that relationship, that fractal component to them. A lot of plants have that procedure, that idea. I'm gonna try to type something in here. It might not be that. Oh no, that's what I'm looking for right there. Okay, so this type of broccoli. but you can kind of see that. I don't know what person thought, yeah, let's put that in my mouth. For the first person that ate that, like, that doesn't look safe to eat. But you see the fractal idea there, right? Okay. And in nature, so a lot of times in nature, things kind of start to position themselves using the Fibonacci relationship. Okay. If we were to investigate like a sunflower, the part where the seeds are, okay, it's going to kind of look like that, kind of spiral-ish, right? There are fractals that follow kind of a Fibonacci sequence pattern. Okay, so I want to talk about these because it's another place where a lot of our fractals, a lot of these things here, are their inputs to create them are complex numbers. Okay, and then obviously their outputs are complex as numbers, and then we graph those positions. But there's a use for complex numbers. DNA, how DNA kind of balls itself up, is kind of a fractal idea or concept. Okay, so I just always thought that here that they're showing you kind of an image of a coastline. Okay, you can start a fractal is the idea of kind of starting with an image. Where was that last one I had? Okay, so here we start with just an equilateral triangle, and then we halfway through on each side as we create a similar equilateral triangle, right? And we attach it, and then we do that again, and then we keep doing that, and we do that infinitely many times, meaning that when I look at this is the idea of me being able to zoom in. If I was able to zoom in on this one, on each one of those smaller triangles here where my cursor is, there would be kind of this picture again. Does that make sense? And you just keep zooming in and seeing that over and over and over again. Okay. There's some pictures. This was the site that I had earlier. You can kind of see different relationships. Something I read earlier is that they use compressing images, JPEG files, stuff like that, to make them smaller, to send them over data lines. They use a fractal idea to compress them, decompress them, that kind of stuff. Okay, so I think that's kind of interesting. But I think, guys, doing what we're doing today, what we've been doing the last couple days, I think it's vague. It's abstract. It's weird. Well, what are we doing this for? Okay, I want you to know that there are real life applications of working with complex numbers. Okay. And I just, from my viewpoint, I didn't know that stuff when I was in high school and I was doing this stuff. Even when I got into maybe the lower level math classes in college, where we're using complex numbers and just doing the arithmetic, I think it makes more, or it is more meaningful if you understand where that arithmetic is targeting or what it's targeting. It wasn't until I took it's called complex analysis, basically analyzing complex numbers in the complex number system in my graduate courses that I really started to understand purposes of complex numbers. And what kind of sucks, though, is that I've got that knowledge, but you guys don't have the same math knowledge that got me there, because it was like 7 years of math, to be able to kind of really explain and show you like singularity points and stuff like that, in which complex numbers are really useful in the calculus that complex numbers are really useful for. I think, and you've heard me say this before, I think math sometimes is backwards. You go to Algebra 1, you start using the quadratic formula, right? Use that in Algebra 1. It wasn't until the beginning of this year, or maybe the end of Algebra 2, that you started to realize what the quadratic formula was derived from. Like completing the square of ax squared plus bx plus c equals 0, right? But you'd been using it for maybe a year, 2 years, 3 years before you actually learn why you can use it or what it was used for. I mean, there's things that we can do arithmetically, but at the same time, maybe we don't have enough math knowledge to really apply it and see its use until later. I think this is one of those things. Yesterday we said z, if z was equal to r cis theta, then z to the n was equal to rn cis n times theta, right? That right there is de Moivre's theorem. Okay? I want to do something. Let's say now this is kind of weird using this note. Say let me do this. Let's say instead of using n for this, could I have said z to the let's just use u. Z to the u is equal to r to the u, and then that would give me u times theta. Does that make sense? Okay. But let's say u is 1 over n. Then wouldn't z to the u equal z to the 1 over n? Then it'd be r to the 1 over n, right? Times cis. Now u is 1 over n times theta, which that ends up being r to the 1/n cis of n, not n, theta over n. Does that make sense? Okay. Now, what that ends up being then, guys, think about this. What is z to the 1/n the same as? Isn't that the same as the nth root of z? Is then equal to the nth root of r times cis of theta over n. And if we do it that way, if we go through this procedure here, what happens when we divide by n there is we take our theta and we've started to reduce it by quite a bit, depending on what n is. And we should know that, if I give you theta to be 45 degrees, I can add 360 to that, you get 405 degrees, right? And I give you the same point, correct? Same terminal location. Well, if I take theta divided by n, now, when I add 360 to that theta up top, I'm going to get another angle that is inside one revolution of 360 degrees. So, I guess that argument, and it'll make more sense here in a moment when we start doing a specific example. The nth root of z is actually equal to the nth root of r times cis of theta plus 2 pi k over n. And that 2 pi k is when k is equal to 0, 1, 2, all the way up to n minus 1. And basically what that's going to do is say, okay, well, if n is 3, okay, we take theta divided by 3, you now have a pretty small angle, and if you were to add 2 pi k over 3 to that, you're going to get another point inside one revolution of 0 to 360 that will satisfy what we call the nth root of z. Okay? So we'll see an example, and I think that argument part of adding 2 pi k over n will make sense. Hopefully the idea at least to here makes sense. Because yesterday we were just raising to the nth power, right? And we take r to the n, and we take theta multiplied by it. Well, now it's just 1 nth power. We do the same thing. Raise r to the 1 nth, multiply theta by 1 nth. Or whatever. So, we call this finding the nth roots of z. Finding the nth roots of z. So basically this is saying, okay, if I have an a complex number like 2 plus 2i, and I'll take the square root of that, we can do that now. Okay? In rectangular form, can't do it. Okay? But polar form, we absolutely can. So here's what I want to do. I want to start with let's just go. Maybe I'll do the same one last class did. We're going to say Z. Usually they'll say is negative 64, but I'm going to write this negative 64 plus 0i. Now, obviously, plus 0i, you wouldn't ever write that, right? But I do want to convince you that this is a complex number. And obviously they're using Z here, so that should be an indication of it as well. And they'll say, fine, so they'll say if Z is equal to this, find the sixth roots of Z. So basically it says find the 6 things that if you were to multiply them individually by themselves 6 times, you get negative 64. Okay? In order to do that, we are going to have to take Z, which is in rectangular form right now, and we're going to put it into polar form. Okay? So remember, in polar form, your radius is a squared plus b squared, right? Now it's a distance, so the fact that a is positive or negative doesn't really matter. Same thing for b. So if I do this, a would be 64, we'd square that, plus b would be 0, we square that. So it gives me square root of 64 squared. So r is just going to be 64, right? Hopefully that makes sense. If I were to graph that point, negative 64 plus 0i, if I were to graph that, zoom out, is that on a circle that has a radius here of negative 64? Okay, so that should make sense. Now theta, okay, look at here. It's easy if we look at this picture. Theta would be the angle from the positive polar axis to z sub 1, right? How big is that angle? 180 degrees, right? Or pi, whatever you want to use. Now, if you were to use this formula, theta is equal to tangent inverse, you'd have b over a, so you have 0 over 64, which gives me 0. And no matter what calculator I use, if I type in the arctangent of 0 over 64, or just 0, what's it give me? It gives me 0 degrees, right? Yet that does not get me to negative 64 plus 0i in the coordinate plane. So we need to realize that that is actually 180 instead. Okay? Okay. So now, with that stuff, we should be able to find z in polar form to be r. Cis, I'm just going to write this as pi. 64 cis pi. All right? Okay. So now if it wants us to find the sixth roots, what that means is that you're going to apply this formula. Z to the 1 over n is equal to r to the 1 over n cis theta plus 2 pi k over n, where k 0, 1, 2, 3, all the way up to n minus 1. Okay, so this is the z that we're going to do that with. So we'd say z to the 1/6 is equal to 64 to the 1/6 times cis theta is pi plus 2 pi k. What is n? n is 6. That n right there tells me that in this particular case, n is 6. And then we'll go k. What are the values of k that we have to use here? Now we stop at n minus 1, right? So if n is 6, we stop at 6 minus 1. Okay? And what that does is since we started at 0, it's that k again is an index or counting tool. If I started at 0, that is the first solution. It's the first sixth root. And then moving on to 1, 2, 3, 4, 5. If I look at those, I will have 6 total solutions, right? 6 total roots. Okay. The process then goes like this. They start to, instead of using z anymore, when I want to find my nth roots, and this is just something that I've seen in WebAssign, they will start using now w. Once you find the sixth, so w sub 0 will be one of my 6 roots. Does that make sense? W sub 1 will be another one. W sub 2 will be another one. Okay. So sometimes they will write it. So this here, let's kind of do this. This is 64 to the 1/6. Anybody know what 64 to the 1/6 is? It's 2. Okay. So 2 cis. Okay. Now this will be pi over 6 plus. I'm just going to write it this way. You can reduce it if you want to. I think it's going to make more sense to write this way. Okay. What they'll write is that is w sub k, meaning that's a rule for finding the kth roots of your complex number. Okay. So it's going to give us our 6 different roots. And it just allows us to say, okay, well, if that's a rule for w sub k, what do I do when k is 1? Well, it's going to be 2 cis. If k is 1, sorry, k is 0. If k is 0, that goes away, right? So you get 2 cis pi over 6. When k is 1, I get 2 cis. This is the reason I didn't reduce this. If k is 1, this is 2 pi over 6, right? And then give me this to be 3 pi over 6. And I'm not going to reduce that right away because of this fact here. I'm going to go k being 2. I'm now going to add pi over 6 and 4 pi over 6, right? It'd be 5 pi over 6. And now, and I can recognize this right away if I, between w sub 0 and w sub 1, I want to do 3 this first time. What do you see is happening between pi over 6, 3 pi over 6, 5 pi over 6? Yeah, you're just adding 2 to the numerator. You're adding 2 pi over 6 to the whole thing. This is an arithmetic sequence in regards to the argument. So instead of just blindly substituting and evaluating this argument every single time for different k values, be intelligent about it and say, okay, well, I'm just going to write all this stuff, 2 cis the same, but now the next one, add 2 pi over 6. Add 2 to the numerator. The next one, w sub 4, will be 2 cis 9 pi over 6. And w sub 5 will be 2 cis 11 pi over 6. Okay? Now, that's all great and true. The next thing we do is that we're going to actually convert those back to polar coordinates, or sorry, rectangular coordinates. Okay? Because right now I want to see what are, and if they gave me negative 64 in rectangular form, a plus bi form, then I want the 6 roots in a plus bi form, right? Does that make sense? It's not too bad with this one. Remember that each one of these, so move that over a little bit more. Remember what this means here. It means 2 times cosine of pi over 6 plus I sine of pi over 6, right? Okay. Now we do that for this first one here, but the next couple I'm going to kind of glaze over the expansion of that. Okay, what is the cosine of pi over 6? Radical 3 over 2, right? What's the sine of pi over 6? 1/2. If I multiply those things by 2, what happens to the denominators? They cancel out, right? I see get radical 3 plus I. Okay? So, this first W sub 0 is equal to radical 3 plus I. What does that mean? That means if I took radical 3 plus I and I multiplied it by itself 6 times, so radical 3 plus I times 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 radical 3 plus I. I FOIL all that out. It's going to condense down to negative 64. Okay. Now I'm going to do the same thing for W sub 1. Okay, so there's not a real nice way initially to start like seeing a pattern here. There are patterns that you can recognize maybe after you've got all 6 of these written out, but I don't know that I would try to develop any understanding for a pattern in trying to quickly convert these back over to rectangular. I would just go 2 cosine of 3 pi over 6. What's cosine of pi over 2 essentially? 0, right? And then what is the sine of pi over 2? 1. So does it make sense that I take that 1i and multiply it by this 2 here? Okay. What's the cosine of 5 pi over 6? Negative radical 3 over 2, right? What's the sine of 5 pi over 6? 1/2. Multiply both by 2, you get negative radical 3 plus I, right? There's a little bit of a pattern of symmetry here with that point and that point. Okay. What's the cosine of 7 pi over 6? Negative radical 3 over 2, right? Times 2 is negative radical 3. What's the sine of 7 pi over 6? Negative 1/2. Negative 1/2 times 2 is negative 1. There's symmetry with that point and that point now. Okay? There's relationships between W2 and W3. Okay? But again, I would not use those relationships to help kind of generate the other point. I think it's just a little bit maybe confusing to do that. All right, so let's look here at this last 2. If I go 2 cosine of 9 pi over 6, 9 pi over 6 is 3 pi over 2, right? 2 times cosine of 3 pi over 2 is 2 times 0, so it goes away. Sine of 9 pi over 6 is negative 1, so I get negative 2i. So 0 minus 2i. Relationship there, right? And then the last week's 11 pi over 6. Cosine 11 pi over 6, radical 3 over 2. Sine of 11 pi over 6 is negative 1/2. So you get radical 3 minus I. Those are my six complex roots of negative 64. So let me type those in real quick here, and then we'll see some relationships. If we take square root of 3 plus I, we had 2i, we had negative square root of 3 plus I. We had negative square root of 3 minus I. We have negative 2i. And we had square root of 3 minus I, right? Okay. Now I'm zoomed out real far. If I zoom back in, I don't want those things. Zoom back in. Those are your 6 roots. Now, what do they all lie on? They all lie on the same circle. Okay. Now, the idea, so we found the 6 roots if we were to maybe, so let's see here. They all had a radius of 2, right? In polar form. So I show a law on that circle. If I were to connect them with chords, Z1 to Z2 to Z3 to Z4 to Z5 to Z6, back to Z1, we would get a hexagon, right? And then if I want to find the 7th roots, 8th roots, 9th roots, that hexagon turns into a octagon, eventually nonagon, decagon, that kind of thing. But the idea is that there's kind of a fractal relationship occurring there. Okay. Okay, so what does all this stuff mean? Remember what this is. This is the 6th root. It's like taking the square root or the 3rd root or the 4th root. At any time, so if I had, let's say, the square root of 25, that is equal to 5, right? That means if I take that number and raise it to this index, it should give me what? It should give me the radicand, right? So we just said that the 6th root of negative 64 plus 0i is equal to radical 3 plus I. So what should I be able to do with that number to get negative 64 plus 0i? Raise it to the 6th power. So let's see if that happens. Let's take z sub 1. So let's do this. Let's go z sub n and raise that to the 6th power. See if this works. So start this at 1, and we'll go to 10. Let's go 1. Yes, I know. That doesn't real. It doesn't. I was trying to get it to call. So like when I let z sub n, so if n is 1, it takes this. So this is not recalling any of these. So that's kind of an issue. But so that's not gonna work. But we should be able to. I just didn't want to type all these in over and over again. But if I go z sub 1, raise it to the 6th power. U negative 64. That says minus 0i, but does that matter? It's negative 64, right? If we go z sub 2 and raise it to the 6th power. Okay. Z sub 3. Raise it to the 6th power. Okay. Now, let's just do this. So z sub 4 to the 6th power. See how I gave you the same number here? Okay. If I go z sub 5 to the 6th power, okay, give me that. And z sub 6 to the 6th power gives me that, right? Are they all, if I raise all of these to the 6th power, do I still get negative 64 in each situation? Okay. There are no other numbers, no other complex numbers, the entire plane, that can raise to 6th power to get negative 64. Those are the only 6. That kind of makes sense? Okay. So let's do one more. There should be, I'm vaguely remembering doing this. I should have tried this with GeoGebra before today. I just figured it was going to work. Maybe I've got an updated version of GeoGebra that took it out or something like that. But I swear I remember last year typing in like negative 64 plus 0i as z sub 1, and then taking that and raising it to the 6th power, and it generated all 6 roots. I don't know why it's not doing that now, but I'll do a little bit of research during Wildcat time, see See, because I want you guys to have a quick way of checking to see if everything you've done by hand works instead of having to type all of those in. If I type in, this is kind of what I was talking about. If I have negative 64 plus 0 I as Z1, I want to be able to type in Z sub 1 to the 1/6 power. And I want it to give me all 6 of those nth roots, right? It only gives me one of them. Okay. Now maybe we can do some things with some formula stuff here to find the other ones. I think that's going to be more involved algebra than what's necessary. Okay, so I'll see if there's a command that will give me all 6 of those. Let's do one more. Some of these guys, they don't really work out to be real nice numbers. Because obviously we're taking our theta and dividing it by n, and there's only so many thetas that you can divide by a value of 2, 3, 4, 5, 6, 7, whatever. That's going to generate 30, 45, 60, and 90 multiples on the unit circle, right? So a lot of times we don't end up with real nice, clean arguments, and that's fine. When that happens, I think the best thing is to actually manipulate these and work with degrees. So that's kind of what I want to do in this one, is work in degrees. But it says find, if z is that, find 3 cube roots of z. Okay? So remember, that's rectangular. Okay, so R is going to be 4 plus 4 underneath the root, right? So radical 8 equals 2 root 2. Okay. Theta. If this is in what quadrant? 2 plus 2i is in what quadrant? First quadrant. Is 2 plus 2, is that a point that kind of cuts the first quadrant in half? Yeah, so that lies on the line y equals x, right? If we're talking about Cartesian plane. So theta would be 45 degrees, right? If you want to use tangent inverse of 2 over 2, that's fine. It's going to be tangent inverse of 1, which is going to give you 45. So now z is going to be 2 root 2 cis of 45, right? Now I want to find the cube root. So the cube root of z is the same thing as z raised to the 1/3 power, right? Which then you take your r, which was 2 root 2. We're going to raise that to the 1/3 power. And then cis, okay, it'll be your 45 degrees plus k revolutions around the unit circle divided by n. What's n in this case? 3. Okay. Now, I'm going to do a little bit of algebra here. Okay, you see a little bit of it on the board, but I see that and I think, okay, well, you're taking the cube root of 2 radical 2. If that's a nested radical, it gets messy. But because those values of 2 that multiply off front and the radicand are the same number, is 2 radical 2 the same thing as 2 times 2 to the 1/2? And then I'm raising that to the 1/3, right? Does that equate to, now if I have like bases and I'm multiplying, what do I do with these exponents? You add them, right? So does that equate to that? Now if you have a base raised to an exponent raised to an exponent, what do you do with those powers to a power? Multiply them. So it gives me 2 to the 1/2.
Pardon the interruption. Mr. Jesco is currently out of the building. When the bell rings for Wildcat time, we would love for all staff and students to please report to the gymnasium. Once Mr. Jesco arrives, we would love everyone to sing happy birthday to him. So again, when the bell rings for Wildcat time, please everyone report to the gymnasium. When Mr. Jesco arrives, we will sing and hopefully make his day. Thank you.
All right, so that algebra there shows you how to go from 2 root 2 to the 1/3 to, it just ends up being radical 2, okay? Meaning if I take radical 2 and multiply it by itself 3 times, radical 2 times radical 2 times radical 2, does that end up giving me 2 radical 2? Yeah, okay? You could have done the same thing with the radical 8, okay? If I leave a radical 8 and raise it to the 1/3, well, that would be 8 to the 1/2 raised to the 1/3, so it gives me 8 to the, am I doing that right? Yeah. I guess you get 8 to the 1/6. Maybe, you probably don't know this, but now you do. Radical 2 times 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 radical 2, 6 times gives you radical 8. Or gives you 8. Really not something maybe is common knowledge. So doing it with the 2 radical 2 is the best. So now, all I did here is I just took 45 divided by 3, gave me 15, right? 360 divided by 3 gave me 120, right? So this is my formula for finding my nth roots. So if W sub 0 would go radical 2 cis 15, right? W1 is going to be radical 2 cis of 135. And then W2 is going to be radical 2 cis 255. When you do those, okay, so we have square root of 2 cosine of 15 plus I times sine of 15, okay? When you change it over to rectangular form, you're going to get that. Now, because we don't know, I mean, we could go off of, I think 15 degrees is like radical 6, cosine of it is radical 6 plus radical 4 all over 4. You probably don't remember that using half angles or some differences. So you could do this in exact values if you want to, but that's fine right there. Okay, so that's your first one. Your second one will be when this number here is 135. Now this should be a nice one that we know because we know 135 off the unit circle, right? So there's your second, third, or cube root. And then the last one will be when it's 255. So it gives me that one. Okay. Now as we were working through there, obviously it wasn't plotting and keeping Z1, Z2, and Z3 on the plane there on the right hand side, but they would all be on a circle. That means there have to be 3 points on the same circle, and they'd be on that circle that has a radius of radical 2. Okay, so if I go to circle, center 0, square root of 2, radius, all Z1, Z2, Z3s, the 3 cube roots of 2 plus 2i would go on that circle. Okay? My plan for the next couple days is to move on to chapter 9. We're only doing 3 sections out of chapter 8. We'll do 3 sections out of chapter 9, and then we'll have a test of that stuff again. And then that should give us about, 3 to 4 days to prepare for the final. There are a few sections, depending on the days that we have, there's a few sections that Rose doesn't ask us to talk about, and they won't test you over. But I think it's important for you if you're going to go to calculus. And one of those is parametric equations. One of those is talking about vectors in 3 dimensions and that kind of stuff. So if we have enough time, we'll cover those. I won't test you over them, but I do think it'll be a benefit of you for you to see them. But otherwise, guys, we got about 3 sections to knock out with vectors, and this course will be concluded.